Hello everyone, this is the video lecture of section 10.3, the second part out of two parts. Okay, so in the first part we covered up to example 3 where we used this formula for the curvature of a curve. Now this is the initial definition of curvature. Very intuitive, easy to understand, but harder to use because it requires to reparameterize your original given parameterization with respect to arc length. So that is actually hard for many problems. And this one allows us to get the curvature without changing the parameterization. Just do it as it is given, as we see in this example 3. Now there is yet another form, convenient form, of a curvature formula. As you can see here, in order to get t prime, you have to go through derivative, and you have to find the magnitude, and divide your r prime of t by magnitude, and then you have to take the derivative of that. So even though it looks simple, it goes through multiple steps, all right? Now, there is another approach to curvature. This is a little bit harder, but it can be quite useful. So I'm going to write it, this one, without writing, parentheses t of t. Only just 1 minute, okay? And then magnitude of r prime is our ds dt. Okay? Alright. Now, from here, r prime of t is magnitude of r prime times unit tangent vector capital T. Okay? And then, this is ds over dt capital T. Now, let's take another derivative. Then we have to use product rule here. F prime g plus fg prime. So, second order derivative of this times t plus ds dt t prime. And then, let's consider r prime cross product r double prime. Don't ask me why. The reason why we are doing this is that somehow this one gives us very simple, nice thing. So this one is ds dt t cross product okay. Then you get ds dt times d squared ds t squared t cross t plus ds dt squared when you distribute t cross t prime. This is cross product. Now, cross product magnitude is this magnitude times sine theta. That is the angle between two vectors. If you have the same vector, it's 0. Sine 0 equals 0. So A cross A is always 0 vector, right? Now, here, note that T of T is always unit 1. Right? By definition, unit tangent vector. We made it to be always unit vector. In section 10.2, we learned that if a vector is constant magnitude, then the dot product of r and r prime is 0, which means this one, its derivative is always orthogonal, right? Therefore, t and t prime is orthogonal. Then when you are orthogonal, magnitude of t cross t prime is just, right? Sine of 90 degrees equals 1. because it's orthogonal, right? And this is 1. So this is what we are going to do. If we take r prime cross product r double prime magnitude, this is 0, absolute value of ds dt squared, and t prime. Okay? Therefore, t prime magnitude is r prime cross r double prime magnitude over ds dt squared. Now ds dt was magnitude of r prime, so I can write it. What was curvature? Curvature was t prime over r prime, t prime magnitude over r prime magnitude, right? So this one divided by one more r prime. So you get the third power. Okay? So I'm gonna write it, all of these. So 3 different versions here. Kappa dt ds magnitude, which is dt magnitude over r prime of t magnitude. Okay, I'm gonna write it. Now we found that is r prime of t cross product r double prime of t magnitude over r prime of t magnitude third power. Okay? Now, example 4. Find the curvature of the twisted cubic. Find the curvature of the twisted cubic, which was given by t squared t cubed. Okay? So let's use this one instead of going through this process. Okay? So r prime is 1, 2t, 3t squared. R double prime is 0 to 60. So we have to take cross product of these two. So I, j, k, 1, 2t, 3t squared, 0 to 60. So x component is deleting this and this determinant of this. So 12t squared, excuse me, 12t squared minus 6t squared minus of discriminant of this 60. And then delete this and this 2. Alright? So what is it? This will be just 6t squared minus 6t and 2. Right? So we need magnitude. R cross R double prime magnitude is 6 square root of this square, which is 36t to the 4th, this square, 36t squared plus 4. Alright? If you can factor out 4, square root of 4 equals 2. If you want, you can write it. 9t to the fourth, 9t squared plus 1. On the other hand, magnitude of r prime, square root of 1 plus 4t squared, 9t to the fourth. Okay? So, well, this is it. Therefore, your curvature as a function of t, kappa of t is this thing over this thing's third power. You can write it 1 plus 4t squared, 3 over 2. This is 1/2 power of this inside, raising to the third power with 3 over 2. Now, if t equals 0, at 0, 0, 0, which is t equals 0, your curvature kappa is plugging in 0. So 2 over 1, so 2. Okay? All right. Now, this one can be used other situations, more convenient than other forms. That is, let's say, what if your curve is given as a planar curve, y equals f of x. Now, this is given in terms of parameterization or vector value function. Well, then we can, this is the obvious, right? When z equals 0, right? So our r of t, you can have the natural choice of this. Now let's try to find, so x equals t, all right? Then r prime of t equals 1, f prime of t, 0, r double prime of t, 0, f double prime of t, and 0. If you take cross product of these two, I, j, k, 1, f 0, 0, oh, f prime, f double prime, 0, x component, delete this and this, well, determinant is 0, minus of, delete this and this, also determinant of 1, 0, 0, 1 is 0, and z component, AD minus BC, so f double prime. So, r prime cross r double prime, magnitude is square root of 0, 0, this one squared. So it's just f double prime of t magnitude. Okay? And r prime of t magnitude is square root of this square and this square. 1 plus f prime of t squared. Now, therefore, curvature as a function of time is this thing over this thing's to the third power. Now, here t's are same as x. So then I can write it, this one is kappa x. F double prime of x over 1 over 1 plus f prime of x. This thing's 3 over 2. So more or less determined by second order derivative. See, second order derivative is determining concave up or concave down, right? Even though concave, this large value, if it is already high tangent line, high slope, then, you know, from this to this change look like a small, but like a slope 10 to 20. It's large change, but to your eyes, it's a little bit of change. So the larger the f prime value, you have to discount the importance of the largeness of second order derivative, right? So if you really think about it, it really makes sense. Yeah, curvature, all right? How fast it curves per distance. Anyway, so this is another form. This is convenient if you are given xy equation. So, example 5. Find the curvature. Curvature of the graph y equals x cubed at 0, 0, and 1, 1. Okay? Well, this is your f of x. So, f prime of x, 3x squared, f double prime of x, 6x. Your curvature is absolute value of f double prime over 1 plus f prime squared to the 3 over 2. This is just 6 times absolute value of x over 1 plus square 9x to the 4th, 3 over 2 power. Okay? So, then, at 0, 0, your curvature is when x equals 0, right? Plug in x equals 0. So it's 0. When it is 1, 1, then you have to use x equals 1 in the formula. Your curvature will be 6 over 1, so 10 to the 3 over 2 power. Okay? Which is about 0.189, about 0.2. Roughly 1 over 5. That means the way this one curves around 1 is just like a circle of radius 5. So best approximating circle around this will be radius 5, something like this. Okay? The way this one curving is exactly same as, not roughly same as the curvature of the circle with radius 5. Okay? All right. Okay. Now, example 6 is example 5 of your textbook. This is almost same as this one. So now I'm going to leave it to you as a reading assignment. Okay? Example 6 is same as example 5 on page 711. Reading assignment. Okay? All right. Now, recall, we learned that unit tangent vector is constant magnitude 1. That's why t and t prime is orthogonal, right? So then we will define n of t as f prime of t over its magnitude. Again, this is called principal unit normal vector. same direction as t prime. And unit vector, because I divided that one by this one magnitude. So, therefore, because it is same as this direction, therefore, t of t and n of t is always perpendicular. So, and then, therefore, we define another unit normal unit vector, b of t, as t cross n of t. This is called binormal vector. Binormal unit vector. Why is it unit vector? Because magnitude of b of t, magnitude of t of t times magnitude of n of t times sine of angle between them, which is 90 degrees. This is one. Normal vector, this is unit vector, everything is one, therefore this is also unit vector. So, your t, and when you have a curve like this, unit tangent vector here, and then your normal vector n is, think about it. If t is going from here to here, okay, t plus h, let's say t. That means if I draw this one together over here, this one minus this will be pointing that direction. Right? So, this is the direction of t derivative. So, normal vector will be in the direction, yes, we know this perpendicular to this, your normal direction, your unit normal vector is perpendicular to the tangent line, or unit tangent vector, but in the direction of this one is curving, right? And this has a relationship with the force, centripetal force. Something which makes this motion of objects curving, okay? Okay, anyway, so n of t is not only perpendicular to unit tangent vector, but also is in the direction of curve, is curving toward, all right? And then your normal unit vector will be right-hand rule going this way. So, as you can see in figure 6, page 712, all right? They gave you some examples. You see? T in the direction of you're going, tangent vector, unit tangent vector. So the curve is slightly curving, southeastern direction. That's why your normal vector n, principal unit normal vector is, pointing toward southeastern direction. And then t cross n, I realized t cross n, so t is going here, n is going down there, tn is going toward that direction. So that one is going forward a little bit to the left, okay? Or b of t, by the right hand rule, right thumb's rule, okay? All right. So next example, let's find these three important unit vectors. They make three orthogonal, three orthogonal vectors to each other. Example 7, which is in example 6 on page 712. That is, find t of t, n of t, and b of t of the curve represented by this. Okay, helix again, right? All right. So we have to find t first. How do you get t? T is r vector over is r prime over its magnitude. We have to find the derivative. And we learned that we have been doing this for many times. This is constant square root of 2. So t is r prime of t over this known magnitude is 1 over square root of 2 minus sine t cosine t and 1. Okay? Now, so this one down, second to go, t prime minus cosine t minus sine t and 0. Okay? And we need to divide by this magnitude. What is the magnitude? Magnitude of this one, right? Just constant multiple of this magnitude. Well, this magnitude is square root of cosine squared plus sine squared. This is going to be 1. So 1 over square root of 2. Right? Therefore, your normal vector, principal unit normal vector is, what is it? This one over magnitude. This one divided by this. So these two cancel. So minus cosine t minus sine t, 0. So in this helix, your principal unit normal vector is pointing towards actually z-axis. Think about it. So here, at any point here, you are pointing towards, look at this, z-axis. Over here, your t is over here, and your n will be pointing toward the z-axis. See, kind of opposite of this, right? Except for this t, right? And then your binomial vector will be going this way. T and n is going upward, but a little bit this way. All right? That will be our B. Binomial unit vector will be T cross n, which is I, J, K, T. So that will be square root of 1 over 2 minus sine t cosine t 1 cross product n minus cosine t minus sine t 0. So t, which is this cross product minus cosine t minus sine t 0. I, J, K minus sine t 1 if you do that, delete row and column, determinant 0 minus minus, so sine t. Minus of determinant of delete this and this, so this one, 0 minus minus, so cosine t, so minus cosine t. Delete this, sine squared t, minus minus, plus cosine squared t, so 1. Okay? So this is your binomial unit vector. Okay? All right. So then I'm going to give you a few definitions just so that you can do some homework problems. But this is not that important. We don't want to go further than this. First, the normal plane of the curve C. Normal plane of C at P is the plane through the point P and determined by N and B at the point P. So it shows you that when you have this helix over there, tangent toward the z-axis N and your normal vector B. All right? Binomial. Then going through N and B means that it's perpendicular. The determined by this means parallel to these two vectors. That means with a normal vector to the plane with t. Okay? So plane through the curve perpendicular because your plane is perpendicular to the tangent vector to your curve. So perpendicular to the curve itself. Alright? So we call it normal plane. Likewise, we define the osculating plane of C at P is the plane through P determined by T and N at the point P. Therefore, so this time you're plane generated by T and N. So your curve is tangent to that plane generated by T and N. That means your binomial vector is your normal vector. So a plane with a normal vector with a normal vector B. Okay? Osculating plane. So the thing is that your oscillating plane is where your curve is tangent, right? Now, if you draw a circle on the osculating plane, okay, after this is not going to be, this is a bit too much. So I'm going to just, okay, I'm going to write it and then explain. Third, so before I continue, let me check recording one more time. Okay, so here, 3. osculating circle, or circle of curvature of curve C at P is the circle on this osculating plane. This osculating plane. Which lies on the concave side of C, which means i.e. toward N points. This one points. Okay? Which lies on the concave side of C and has the same tangent line as C at P and has the radius rho 1/kappa. You remember curvature of a circle is 1 over its radius. 1 over its radius means same curvature. So this is a circle which has the same curvature as this curve C at point P and residing on the osculating plane. Same plane as your curve tangent to. And this side. So your osculating plane to the, so your oscillating circle will be something like this. Okay? On the oscillating plane will be like, circle will look like this. Okay? On the oscillating plane. At P. All right? That's osculating circle or circle of curvature. Now, the remark. The osculating circle, of C at P has the same unit tangent vector and principal normal vector. Call it principal unit normal vector. And the same principal unit normal vector. Basically, T and N. They have the same unit tangent vector and principal unit normal vector as the curve C. As C. Okay? As C at P. Which means this is the best approximating circle to C at P. Among the circles, this is the best approximation. Best representation of the curve. Okay? And you could say that the tangent line of C at P we call it first order approximation. Approximation. Or linear approximation. Tangent line is linear. The osculating circle. The osculating circle of CFP is second order approximation. Okay? All right. Which has the same curvature, same tangent line, same unit normal vector. Okay? All right. This is the, and then example 8. Same as example 8 of on page 713. It's a reading assignment. You just have to follow through the calculation. That's all. Okay? All right. This is the end of the second part of section 10.3, which is the end of the section. Okay? Thank you.